The next thing that we're going to begin talking about here is free fall. So free fall is a specific situation where objects are in midair, okay, and only gravity is acting on them. We'll talk about forces a little bit later on, but for now all you need to know is free fall is going to occur anytime an object's in midair. It could be falling or it could be rising, okay? It doesn't necessarily have to be falling because it says free fall. The key is it's just in midair with nothing else touching it. So when this is the case, when an object's in midair, either freely falling or freely rising, here's what we know, and this is a pretty big concept that we're going to keep coming back to throughout the year. All objects, regardless of anything about the object, their mass, their size, whatever, all objects accelerate at the same rate towards the center of Earth due to gravity. Every single object. This does make an important assumption here that we are assuming there's no air resistance. Okay, but in the absence of air resistance, every single object is going to accelerate towards the center of the Earth at this value, g. So g has this value here of 9.8 meters per second squared. If we're talking about an object on or near the surface of Earth, it does vary if we go to other planets, but we always refer to that acceleration due to gravity on or near the surface. We refer to that as g. So on Earth, it's 9.8 meters per second squared. If you go to the moon, it's about 1.6 meters per second squared. Mars is like 3.4 meters per second squared, but they're all g. They're all the acceleration due to gravity. And this idea of all the objects accelerating at the same rate, that's going to be true on any planet. The actual value for that rate will change, okay? But in the absence of air resistance, all objects are going to accelerate at the same rate towards the center of any planet. And on Earth, that rate is 9.8 meters per second squared. All right, for this next part, we've talked about the really, really big important concept, and that is that all objects accelerate down at 9.8 meters per second squared. But we want to get a little bit more specific. So we're going to consider a situation where we have an object that rises up to its peak and then falls back down. And we want to think for a second about the following three questions. When is the object speeding up? When is the object slowing down? And what happens at the peak? So when is the object speeding up? You can probably just think back to some experiences you've had with objects rising up in the air and falling back down. And that should tell you that objects speed up when they are on their way down. And we can think about this, going back to what we talked about before, we can think about the direction of the velocity when it's going down, which is going to be down, and the direction of the acceleration, which is down the entire time. And we can see here that we have velocity and acceleration in the same direction, which means we're going to be speeding up. The reverse of that question, when is the object slowing down? That's going to be on the way up. Once again, thinking about the direction of the velocity and the acceleration, when it's rising, the velocity is going up as it goes up to the peak. The acceleration is going down, okay? And so this right here, when velocity and acceleration are in opposite directions, is a case of slowing down. Last question, what happens at the peak? And this is a really, really important situation to talk about. So, as this object is rising to the peak, and we're going to think back to some of these situations with motion graphs, we have an object that's slowing down, slowing down, slowing down, slowing down, hits this point, and then begins speeding up in the opposite direction. So a few very important things happen here. The first thing that happens is at the peak, the velocity is zero. We're slowing down, and eventually we hit a stop. We hit this point right here where we no longer have any velocity, okay? And then we change directions, okay? So that's another important thing that happens. The question, though, and this is a common misconception, is what happens with our acceleration when we're at the peak? So we're rising up to the peak. What is our acceleration? And a lot of people want to say it's zero, but we're actually still accelerating down. And there's two ways that I think about this. Number one, think about for a second what causes that acceleration. Gravity is the thing that ultimately causes that acceleration. So if you're going to say that the acceleration at the peak is zero, you're saying that gravity magically shuts off when the object gets to the peak, and that obviously is not the case. The second thing that I always think about is if we had a situation where our velocity was zero and our acceleration was zero, what would happen? And the answer is nothing. If something is not moving and not accelerating, it's not doing anything, it's stationary. So if that were the case at the peak here, we would see objects rise up to the peak and magically stop. And that obviously does not happen. Okay, you don't need to know physics to know that that's not something that happens in everyday life. So at the peak, we have zero velocity, but we are still accelerating down. And this is the point there at that peak where we are changing directions. Okay, so that is what's happening. And this is no different than some of the other situations we've looked at where an object changes directions. Still accelerating, but it hits that point just for an instant where it has zero velocity. All right, so on the last slide we talked about a few concepts. We're going to talk about a few more here. Free fall is a little bit trickier than regular kinematics because there's a lot more concepts. There's a lot more numbers and things that you need to know without being explicitly told them. So it's going to make things a little bit trickier. So the first thing, though, we're going to start with is talking about acceleration. We know our acceleration whenever we're in free fall the entire time is 9.8 meters per second squared, going down. That does assume we're on Earth, but that's going to be for majority of our problems. A few other things. Number one, we just saw on the last slide that our velocity at the peak we know is zero. Okay, so that's an important concept that occurs right up here when we're at the peak. All right, there's going to be a few other things, a few other concepts that we need to know, and a lot of these we got from that activity we did in class. Now, a few of these are going to be only true if it is what I call a symmetrical launch, meaning that it goes up and returns to the same spot. So that would basically be cutting it off right here. It returns to the same height that it started at. But if that's the case, okay, and I'm going to write all these in blue, if that's the case, if we do have symmetry, there are a few more concepts that we know. So the first thing we know, if it's symmetrical, is that the time is 1/2 the total time when it gets to the peak. So we have this example over here with a ball going up, rising to the peak, and coming back down. And we see that in this case, it takes 3 seconds to get to the peak, and then another 3 for a total of 6 seconds to return back to that same spot. So our time at the peak here, we know is always going to be half that total time. And that's a pretty useful concept in a lot of problems. Another thing that we know is that when we're down here, our velocity is going to be the negative of our initial velocity. So whatever speed we initially have, in our example over here, it's 30 meters per second. When it returns to that spot, it will have the same speed, but it'll be going down, so it'll be negative. Okay, same speed, just opposite directions. And we actually see that at any 2 points that are even, the velocities are the same. Okay, whether it's 20 and -20 or 10 and -10, the velocities are the same. The only thing that changes is the sign, because the directions are different, whether it's going up or coming back down. And the last concept that we know, and this occurs at the end again, and once again, this is only if it's symmetrical, okay, but the last concept that we know is that the displacement, when it returns to this point here, is going to be 0. And that makes sense. That's really just the definition of returning to where it started. But if an object goes up and comes back to the same point that it started at, its displacement is going to be 0. So there we have 3 additional concepts. Only true if it's symmetrical. All right, so once we get down here, okay, and we get past that point, all right, whether it's on the example to the right or our little diagram, once we get past that point, or maybe if we ended up here, these wouldn't be true because they're not symmetrical. But if it is symmetrical, we have 3 additional concepts that we know. No matter what, we know that the velocity at the peak will always be 0, symmetrical or not. And we know our acceleration on Earth will always be negative 9.8 meters per second squared. So those ones we know for sure. These other ones depends on the actual flight path. So we're going to practice applying some of these concepts and actually solving some problems in class.